I bet the door will open as soon as I start talking. Okay, let's try it. So 12:31. Okay, you count the seconds when the door will open. So the main topic today is what is called the elimination algorithm. That we have sort of seen it with examples up to now, but we're going to try to do it in a sort of graph theoretic manner. But before that, I need to cover maybe a few slides from the previous lecture. If you remember, we're talking about, you see, I was right. Okay, so we are going to talk, it was not about you. Okay, so we're going to talk about examples that actually, some of them we will see in very fine detail. So if later on, so if things look weird in the context of Bayesian inference, for those who have not seen these things, we will come back to those things later on. So the example that we already did was one of polynomial regression. So this is actually just Bayesian linear regression. So we fit the response of the system, which is scalar, and we call it T, to some polynomial with this coefficients Wi being random variables. And we wrote the joint probability distribution like that. So this is the prior on W, and this is the likelihood. So if we knew W, what's the probability of Tn, okay? This is in its most general form, all right, where W has, the prior on W has some hyperparameters alpha, and this likelihood model for each input, for each W, depends on some noise variance sigma square, which is not known. So this is sort of, again, in more detail, the joint probability of T and W. T is the response, and W are the unknown regression coefficients. So what we did is we introduced this plate notation, and everything you see inside the box means it is repeating n times. So when you see here, you know, when you try to write the joint probability distribution of all the variables on this model, you're going to have the probability of Tn given xn, but now you have n of those, and that's how you get this product. And of course, you have the probability of W given alpha, and alpha and sigma square are taken as fixed parameters right now, so there's no probability affiliated with them. So this is the plate notation, and when you get experts in this type of things, somehow you will be drawing this picture here, and immediately implying this, rather than writing this and then saying, here is a picture showing the distribution. Okay? But it will take some time, basically, to get trained on doing that. But in a lot of papers, people don't want to solve the algebra, so what they saw is this, and that implies everything you need to know. Okay, and I think we also extended this, you know, in the last few seconds of the presentation last Thursday, to include also predictions. So this is the joint probability distribution of W, of the training data. T bold is the training data corresponding to X bold, and also we have the predictions T hat corresponding to X hat. So if you try to form this joint distribution, basically what you have is, this is the posterior of W. This is what we had before, but also now you see the likelihood corresponding to X hat, okay? So this is the probability of T hat given X hat, and given the parameters W and sigma square. And again, pictorially, we have the same thing as before, but now what we have done is we have included a node that will allow us for any X hat to figure out what the prediction T hat is. And you notice this prediction T hat depends on X hat, it depends on W, and it depends on sigma square. So the arrows basically show all the dependencies that you need to know. So it looks a little bit complicated, right? But on the other hand, someone would say this is complicated already. Well, this incorporates the whole model. Again, if you have not seen these problems in the context of regression, it will take you less than 20 minutes to read my regression lecture from last semester, or looking at a book like Bishop's or Murphy's to get some idea on this type of things. All right. This is another regression problem that goes with the name relevance vector machines. We actually, I don't believe we covered this even in the course last semester, but it's basically a simple idea. It's similar in many ways to the previous model, but you notice now there is another plate around the W's, and this hyperparameters alpha, they're inside this plate, which means there must be some prior on W that looks like that. All right, so this repetition, so we have MWs. All right, so when you look at this picture, obviously it implies for each of these WIs, I am putting its own prior, and effectively they are the same type of distributions, let's say Gaussians, but the variance is different. And the idea of these relevant vector machines that is not coming in this picture is that somehow when some of these alpha i's go to infinity, this distribution peaks around 0, and basically this W is becoming irrelevant in the whole picture. So this is what is called relevance vector machines. It tells you from all the input variables which ones are needed to do predictions. So similar to what we had before, right? Again, this is the noise variance in the model. This is your sigma square. But now the W has another plate that comes outside to introduce this sparsity-inducing prior model of W's. This model is sort of very simple but very powerful, and allows you to program it actually literally in 5 lines. So it's a very favorite model. If you want to test sparsity and do regression, this is the type of things you want to do. On the mean? Well, so basically we just, we say, let's say if this is a Gaussian, right? This Gaussian is going to be centered around 0. 0 means that W is not important, okay? And with some confidence basically defined by this precision alpha I, okay? So nothing, just, okay? All right. And again, this plate notation does not show what type of distributions are. So, if you want from Gaussian to go to, I don't know, student T distribution, something like that, at this point you can do that as well. So this is a little bit more generic. Okay, so that's the plate notation. We're going to discuss, we're going to spend maybe a whole week on hidden Markov models and state space models. So you're going to see these things multiple times, okay? And I'm going to bypass this unsupervised learning problem under the name of principal component analysis. Maybe we will cover this in a lecture later on using graphical representation. But let me concentrate on either a hidden Markov model where basically all the variables are discrete, or in state space models, which basically they are similar to hidden Markov models, but these x's are continuous variables and the observations y are also continuous variables. And what I have done here, just so I can sort of make things to look a little bit complicated, I'm not simply extending this hidden Markov model to a state space model, but I'm extending it to what is called a switching state space model. And again, I'm talking way ahead of of the course, but I want you to see this thing early on. So effectively, this axis is the hidden state, similar to what you have there. Y are the observations, and S is sort of a discrete variable that tells you, if you think of this representing, let's say, some mixture of models, and the state, let's say S1 can be 1, 2, or 3, so you can be in 3 different components on the mixture. So this discrete variable S1 defines basically both the evolution, the dynamical system, how you go from x1 to x2, but also defines the observation, how you get y1 from x1, okay? And here, this discrete variable S also evolves the same way as you do in a hidden Markov model. And the U that you see on the top is sort of a forcing, a force term. So for example, if this is in robotics, you know, maybe it will be some power input or some force input, torque or something like that, that you put in the model. So this is the generic thing, and this is one of the extensions. There are infinite sort of extensions like that. And the good news are, or the bad news for those doing a PhD, is that all of these models basically have been addressed 20 years ago. Okay? So they may look complicated, but they're all done deals. And actually, they have revolutionized areas from robotics to animation, to just mention it, navigation, satellite tracking, and all of these things. So, all right, so, but I'm giving you this as an example again. What you see here, we're going to spend more than a week or two later on in the course. So what I wanted to do is I just wanted to show you how parameters come in these models, again, as a background. So what I'm doing here is I'm writing the joint probability of x and y in a state space model explicitly. So this is node x1, so you start with p of x1, and then p of y1 given x1, then p of x2 given x1, and then p of y2 given x2, etc., etc. All right, so these are the hidden states you want to compute. These are the observations. You can think of them as noisy, or, you know, they are basically noisy values of x, if you like, in some sense. If the dynamics and the observation models are Gaussian, this problem has a very nice analytical solution. That's what the Kalman filter is, all right? But it can be a mixture of Gaussians, can be anything, and actually we know how to deal with all of these problems, and we will talk on these things later on. But this is what I wanted to show you. These models, so when you say dynamics, you go from xi minus 1 to xi. Obviously, you're going to have to define this distribution, and usually the way you will define it, if, let's say if it's a Gaussian, you're going to have some unknown parameters like mean and variance and things like that. And similarly for the observation model, you're going to have some unknown parameters, okay? And you notice here, the way that I define the state space model is that these parameters theta and these parameters psi, they are shared from all the conditional distributions across the time. So basically the parameters that define, let's say, the dynamical model of how you go from x1 to x2 and x3 to x2 to x3, etc., the parameters psi are the same. Okay, so this is sort of what is called parameter tying, you know, so you use the same parameters to describe the dynamics and the same parameters to define the observations. Obviously not very realistic, right? You can think, you know, a satellite that goes in normal motion suddenly starts accelerating, or something happens, it starts falling, so you don't expect the same dynamics at all the time. So these parameters obviously have to change with time, but if you really want a trivial case, this is how the graphical model will look like. Okay? And what I wanted to point on this diagram, and this is going to turn to be a problem later on in the course, is when you look at this direct graphical model, it has loops. So on one hand, you use the same parameters, so obviously you save lots of computation, seems like. You know, we will see this when we discuss inference. But on the other hand, you can see there are loops, and loops are not good for you. Okay, loops are not good for you. I mean, at least the loops, if you remove the arrows, right, you can see there are loops. Okay? And this will create, it will make inference a little bit more expensive than normal. Okay. On the state space models, you can have multiple chains, and you can see an example here of a factorial state space model. So if you think that each of these hidden states on the first chain can take m values, and this can take m values at each time. So you basically have m cubed configurations at each time. And it comes out, this is the only message I wanted to show you here, is that if you have a model that looks complicated like that, it's actually much cheaper to do inference than having one chain that has m to the cube configurations. All right, so here I have m values, possible m values. So I have m to the cube, possible states. If I substitute this with one chain only that can take m to the cube values, all right, that's way much more complicated problem because it's m to the cube, okay? So we will discuss about this factorial state space models, and maybe we will give you a homework to work on later on in the course. Again, we will do all the details and inference on this type of things. Maybe in 3 lectures or 4 lectures we'll come back to this problem. All right, so I'm going to finish the lecture from last week with one very specific example of inference when everything in the graph is described. So what is not described are the conditional probability distributions. But the actual values of the, we provide basically information data for the actual realizations of the random variables in the nodes of the graph. Okay? And I'm going to address this problem, not in this slide, but in the next slide I'm going to do an example where all the variables are discrete, and I will give you a very specific sort of calculation in 2 slides on how things look like. All right, so we have a graph where I have given you n realizations of the nodes, of the values of the random variables of the nodes. So each realization is a value of each node, and I give you every node, so there's no missing data here. All right, I describe completely, for each I give you all the values of xi's. So the likelihood of the model, so D means data here, we're going to use this as a notation in the course. Theta will be the unknown parameters that define the conditional distributions in the graph, which we don't know what they are. So the likelihood is, assuming IID data, all right, is the probability of xi given theta. Xi, again, is the ith data case and involves all the nodes in the graph. And then what I do is I use the factorization of the graph to write the probability of xi given theta as the product over all nodes of the probability of, for the I case of node t, given its parents and the parameters theta. Nothing fancy, right? I mean, that's how we factorize in directed graphs, right? So, again, the I means that's the data case I, so you can remove I when you think of the second term. The way we factorize is the product of the probabilities of the x at its node given its parents, and here comma the parameters because we don't know what the parameters are. So what I'm going to do now is I am going to reverse the product over the nodes and the product over the data sets. So I'm going to put the product over the data sets inside, and so I'm going to have this product outside, and then the product over the data sets, it will be operating on the probability of xit given the parents for the I case of t and the parameters theta, and I call this the data associated with the family of node t. Isn't it that the likelihood of the family, the likelihood of the data over the family of node t? So if you move this outside, right, and you have product over all the nodes, and here this refers to t and its parents, so isn't it really the likelihood of the family of node t? It only involves the data that have to do with t and its parents. We can see that? All right? So basically, when you look at this equation, the overall likelihood, what does it do? What can we say for the overall likelihood in this problem? That it factorizes over over the nodes. So, even though you have a very complicated diagram, right, the likelihood, okay, of the data, it factorizes over the likelihood, when I say over the nodes, where for each node I include the family of that node, because dt is the likelihood of the family of that node. And why is this important? Because it tells you that this parameter theta t for each node t can be computed separately for the parameter, let's say, theta t plus 1 or theta t plus 2. So you can actually compute the parameters locally for each node because they decouple. Don't expect, by the way, this to be the case when you have incomplete data, but now you notice if from this equation, if you have complete data, you get a product of terms for each node, okay? So the likelihood decomposes according to the graph structure, okay? And if you want to go beyond likelihood and you want to introduce a prior for the parameters, you can make a simple assumption that the prior of the parameters also factorize over the nodes. So basically, this makes sense, right? Because the distribution factorizes and you have every conditional distribution affiliated with a node having this theta t, so you can put a prior that looks like that. And then the posterior factorizes over nodes as well, all right? So you can do Bayesian inference to compute theta t at each node separately. I'm going to give you a very specific example soon, okay? But these two sort of equations are extremely important here. Make a little bit of sense? This is only when you have complete data described. If there are missing data, this is not the case. All right, so it's a different story that we will see later on, but this is sort of a very trivial case. If you have complete data, you can infer what the parameters are by using this decomposition of the posterior effectively over the graph. All right, so I'm going to do one example. And on the next slide, you will see numbers. So if you don't understand this example, you will understand hopefully the slide that comes in because it has specific numbers. So I'm going to consider the case where the conditional probabilities are all given in terms of tables. All right, so we're talking about discrete variables, effectively variables that follow a multi-nully distribution. So let me see what is the multi-nully distribution here. I am looking at node t, and I say the probability of t given its parents is a categorical or multi-nully distribution with parameters theta of t, c. So the subscripts t and c have a meaning here. T is the node that I'm looking, c is the value the parents are. All right? So basically, you can think each row corresponding to the values of the parents, okay? And then what you do is you fit a categorical distribution, okay? So the probability of t, given its parents being a state c, is a categorical distribution. And obviously, in this categorical distribution, you remember you're going to have a number, let's say, of states, and if you sum over all the states, these thetas have to sum to 1. Theta tck tells you basically the probability of being, theta tc1 is the probability of being in state 1, tc2 is the probability of being in state 2, so if you sum all of this you get 1, but remember, theta tck is the probability of being in state k at node t, given that the parents are in state c. Right? So basically you cannot say, you can do the marginal calculation if you want to, but here we are going to, the table tell us the probability of t given the state of the parents. All right? And we fit this with a categorical distribution with these parameters, with this normalization. So let's write this explicitly. Theta tck is the probability. T means, again, node t, okay? We're working at node t. So each node has its own conditional probability. So TCK is the probability that xt takes the value k when the parents k take the value c. The sequence of the indices here, it's arbitrary, right? You could have reversed it. So this is the notation used here. T is the node, k is the value that the xt will take, given that the parents are in state C. We're going to assume that there are kt states for node T. We're going to assume that the parents can be at, can take values of order Ct, so from 1 to Ct, and Ct is what? Is, depending how many parents you have, is the product basically of the states of the parents. So if a node has 2 parents, and this parent has 2 values, this has 3, it will be 2 times 3. Okay? Again, I will show you this in a specific example, but basically this is the how this discrete distributions, these conditional probabilities are defined using a multinull or categorical distribution. So what we're going to do is, and now, you know, I expect that at least you have some elementary understanding of the Dirichlet distribution. If not, send me an email and I will send you a few pages from maybe Bishop's book or Murphy's book to read. But there is really the Dirichlet distribution is the conjugate prior to this multinull distribution. So each of these parameters theta, that's the vector that involves all these theta tck, we're going to put a Dirichlet prior, all right? And then because they are conjugate, the posterior, given the data d, is going to come up to be a Dirichlet distribution with parameters alpha tc defined from the prior plus ntc, where these are vector, right? This is a vector, and this is a vector, and here's the definition of the vector. So I want you to look at it and tell me what this is, using common sense language, basically. T is the node T, K is the probability that, I mean, K is the value, a value that node T can take, assuming that the parents are in state C. So what is NTCK in my data set? Because here what I have done is I multiply the likelihood with this prior. So what do you think NTCK is? And you can look at the definition here. Is the number of times in my data set that node T is in what state? In state K, given that the parents are in state C. Okay? So that's the empirical count. I mean, this is sort of, if you work the algebra, actually there's no algebra, it's just like, so this is sort of the sufficient statistics for this problem. So it's summation over the data set, this is the indicator function, and counts the times in your data set that node T is in state K, given that its parents are in state C. So the mean of the distribution, the Dirichlet distribution basically has, if you check on Wikipedia, you will see what the mean is. For example, for this distribution is alpha tck divided by the summation of alpha tck prime for all k primes. So the mean of the distribution of the posterior comes to be this empirical count plus alpha tck from the prior, and then in the denominator you have this. Actually it should be inside parentheses, even though it's obvious here. So this whole summation here summed over k prime. So if, let's say, you use an uninformed Dirichlet prior where all these alphas are equal to 1, so effectively this is sort of regularization. So you just add 1 in all the empirical counts. So if, let's say, for one state you have no measurements, you're not going to say that state will never happen. By adding plus 1, you make it possible. And that's what this thing does. It sort of tries to regularize this problem for this type of events. All right, so let's see an example. So this is, so we have a direct graph with 5 nodes. And let's say we get some data, all right? And the data basically contain the realizations of x1, x2, x3, x4, x5. And we have 1, 2, 3, 4, 5 data, so n equal to 5. So what I'm going to do is I am going to compute only the mean of the parameters for node 4. So we're only looking at node 4 now, just for demonstration, okay? Only node 4. So node 4 has, you remember this, the parameters now define the conditional of node 4 given its parents. What are the parents of 4? 2 and 3. So what I'm going to do is I'm going to write all possible values of x2 and x3, okay? Obviously, these are binary variables in this problem, I forgot to mention, obviously. So the possible values is 0, 0, 1, 0, 0, 1, 1, 1. And here, I am going to put the number of counts in my data set where node T, the fourth, node 4, this is what T is here, is on state 1 or on state 0, given that the parents are in state C, which is defined on the rows on the left-hand side. You see that? Okay? So let's do one case only. So let's look at the case when the parents are at 1, 1. How many times, look at the data set when x2 and x3 are at 1. How many times k, the node T, the fourth node is at 1. So I see one case here, and I see 2. We agree? Similarly, let's see how many times the node 4 is at k equal to 0 when this is 1 and 1. Let's see, 1 and 1, 0, 1, okay? So it's only 1. And now, immediately I say the probability, if you don't do this prior and you use the MLE estimate, the probability, let's say, of theta TCK equal to 1, I mean, I should actually, I hope I don't confuse you here. When I mean theta TCK equal to 1, I mean theta TC1. That's what I mean, okay? So the probability of theta TC1, the mean value, if you don't put any prior, will be, let's say, 2 divided by 3. But you remember we have to add on the previous diagram, if we use the distributions prior with coefficients 1, we have to add 1 to the counts. So it will be 3 divided by 5, and here will be 1 plus 1, 2 divided by 5. All right? Obviously, the variables are discrete, so not such a complicated problem. But in essence, even if the distributions were Gaussian or something else, you can do similar type of ideas, and do full Bayesian analysis to compute the parameters in the conditional distributions. Now, inference graphs, right? You don't know usually all the nodes. You have partial data, so you know some things, you don't know all the things. So this will be the real problem we have to deal in this class. But if you have complete data, it's an easy problem. And actually, if for those, for example, who use simulation to generate lots of data and then they fit this to models, you may have the case indeed where you describe in the graph, everything, all right, and you have a few realizations, so you can use this type of analysis. All right. So let me drink some coffee and then we will change subject. Today I cheated at Starbucks because they told me the coffee went up to 305. And I said, since when? Because I was there yesterday. And then they say to me, are you a student? And I said, of course. Then 295. So, maybe tomorrow you guys give me your student card so I can hit it, and get my discount. What is that? It's like discrimination, isn't it? Yes. And I'm going to see me again if they ask if I'm a student. All right. Okay. So I'm going to start with the elimination algorithm basically tell you things we already have seen and then try to introduce some graph concepts that will make the elimination algorithm basically easily to program. All right, so now I'm gonna do something sort of a little bit stupid, but you know, we're all mature, so you know, I'm gonna bring maybe if not today on Thursday, also undirected graphs that I haven't really discussed in some details, because I don't want to split this lecture on directed graphs and then 3 weeks later tell you the same things for undirected, okay? So I'm gonna feed in some information that you need to know about undirected graphs and discuss this elimination algorithm for both type of graphs. All right, so you can think, you know, I have a directed graph here. You can think of some nodes that would prescribe them. So this is bolded area, and these are the evidence nodes. These are the query nodes, right? This is what you want to compute. And there are some hidden nodes, and you know, if you want to compute them, you can compute them. But here what I'm going to do is I'm going to call hidden nodes the ones you don't care about. All right? So effectively, this is what you care, x1 given x6. And you understand there are all of these nodes that you don't know. So what you need to do is integrate them out. And I think we already have discussed that the big picture basically looks like the equation you see on the bottom. All right, so we want to compute the probability of xf given the xe, the evidence. And I write this as the joint probability of xf and xc. And that probability can be written as all the probability of all the variables with the hidden variables integrated out. And then here you have the probability of xc, which means you're going to have the joint with xf and xh integrated out. Remember that? Nothing fancy, really. Maybe the notation is slightly different, right? So what we need to learn, and this is what the elimination algorithm is, how can we use sort of graph theoretic ideas to do this effectively? And I think in some of the examples we have highlighted this, but hopefully today, if we manage to finish this, we will see some ideas coming from graphs. Don't need actually this. So let me tell you what the idea is here is. We're going to use the distribution law when we do the summations. So, you know, I give you here an example. You have the summation of some constant times xi. So obviously you can move that constant alpha out and say alpha times sigma xi. So that's one of the calculations we're going to use. And in a more general sense, if we have summation on, you know, think of these discrete variables on the x1, xn, and inside you have a product of alpha 1, x1, alpha 2, x2, etc. Look what I have done. I took this product and I split them in pieces, and then I push forward the summations so each of them operates only on the right argument. So if I want to sum on xn, what's the point of having the whole product and say go and sum on xn that whole product when xn it only appears on the term alpha n xn? All right. So what you do is you push xn all the way in, so you compute this, then you compute the summation on xn minus 1, and then eventually you compute the summation on xn. So the idea is what you see here for performing these summations that effectively will allow us to effectively do these marginalizations, right? This is what the objective is. These ideas are applicable to what they're called commutative rings that come basically together with the operations plus and multiplication. So this is the associative commutative law, effectively generalizing for this elements ABC and this commutative ring, this property that you see here. This is sort of what we take advantage. Okay? So for any A, B, and C where we can do this, so this don't have to be discrete variables, can be continuous, can be, you know, other weird things. Okay? This property, if it is valid, then we can apply this this idea for computing marginalization processes. Okay. Now, obviously, we want to find an effective way for doing the summations because, let me see if there is a count here. If you, let's say that you want to sum, so in this case, let's say we want to sum all these hidden variables out, okay? So let's call the total number of hidden variables is this, all right? So obviously the summation of the hidden variables will result in a computation which will be r to this power, where r the number of possible values that these variables can take. All right, so you're going to have to sum for the r possible values, the r possible values of this, and for each of these, the r possible values of that, and the r possible values of that. So it will be r to the power 8. And I'm not accounting that you would need to do this marginalization for each value, let's say, of the query variables. Okay, but this is, for a big graph, this is a big number, and we don't like it. It will not be efficient to do marginalization. All right. So let's discuss this with an algorithm. So we have a directed graph. Let's say we want to do marginalization on node x6. Okay. So what we want to do. So if you do this in a naive way, right? So the summation will be 6 operations. Well, I'm sorry, 6 operations. If this takes r values, the summation on x6 will be r operations for each of the r values of this and this and this and this. So it will be a total basically of r to the 6 operations. Okay? So let's see a way that is way, way cheaper in performing this, where we don't do r to the 6 operations. So what I have done here is I wrote the factorization on the graph, right? P of x1, x2 given x1, x3 given x2, x5 given the parent x3, x6 given its parents, etc. And then what I have done is I push the summation on x6 all the way to the right, because that's the only place where x6 counts. And the summation of this distribution is actually equal to 1, because it's a valid conditional distribution that is normalized. So how much algebra I have to do? 0, nothing. So if you don't actually do this, you will find yourselves doing r to the 6th when this actually requires nothing. Okay? Now, in general, we're going to see this soon, right? Maybe this, it is not 1, let's say it's something else here. And if it has 3 arguments, doing the summation will be r to a 3rd power, which is still way better than r to the 6th power. Okay, so this is what we need to take advantage. All right, there is a lot on this plot, and actually remind me, I'm going to send you a copy of Jordan's chapter to read this from where I extracted these pictures, okay? So if I forget to do that, bug me before I go home today. So again, the same problem, we want to compute, here we want to compute a summation with respect to node 5. It's more interesting, okay? So what I do is, I take the joint that is factorized like this, and then I am pushing the summation on x5 to the right to include only the terms that depend on x5. And you notice I have included x5 given x3, all right? But x6 given also its parents x2 and x5. Okay? So I have to perform a summation of this term, and we're going to call this a new potential. All right, we're going to give it some name, and I'm going to call the potential phi, and I'm going to put a subscript x5, so x5 reminds me which node I did the summation. Effectively, which node is going to be eliminated. Okay, x5 is the node that I'm doing the summation, and when you sum on x5, what you're left is the potential is going to be a function of x2, of x3, and of x6. So you leave there the arguments that you haven't touched. The rest that you sum, basically, whatever you sum is going to come as a subscript on this potential. Okay? So let's see. So this is the original graph, and it tells you all the conditional probabilities that define the distributions in this graph. You notice this is x3 given x1, x5 given x3, but here you have two parents, so this is a table x6 given x2 and x5. It's a three-dimensional table. So here, all right, let's figure out what the hell this graph says, why it has this blue colors. We're doing a summation on x5, and there will be no more x5, but notice what happens now. x3 and x6 are coming together in a function, which means that they're correlated now. So I have to do what to them? I mean, I see here x3 and x6, they're coming together. All right, so if this is eliminated, I'm going to have to connect basically x3 and x6. Right? So I am not discussing anything yet in the context of the graph operation here, but basically this is the table of x5 given x3. This, when I do the summation, this table will not exist anymore. This is the table of x6 given x2 and x5. When I integrate x5, this will be the summation on this x5 component will disappear, and effectively this three-dimensional table will become actually two-dimensional table, okay? But at the end of the day, you're going to be getting this potential here that is defined in terms of this P of x5 given x3, all right, okay, multiplied by P of x6 given, what is that, x5 and x2, summation x5, and then I get this. All right. So generally, the subscript I you put on these potentials is the node that you're eliminating or you're summing over, and xsi are the dependent variables that come together in the new potential. Okay? The way the new variables basically are coupled, in our case, was x2, x3, and x6. All right. So let's see now this algorithm, not as elimination of variables, but what is called a graph elimination algorithm. So let's try to figure out exactly what's going on here. So let's do the marginalization where we're interested in P of x1 and x2 only. So we need to sum on x3, x4, x5, x6. So I'm going to do the summations one term at a time, starting from the leaves all the way up to x3. All right, and then we will see what happens to the graph. So I leave x3, x4 to x5 here, and I do a summation on x6. So when I sum on x6, all right, obviously the node x6 will disappear. Now, this is equal to 1, right? But let's forget that it is equal to 1. This will give me a potential that I denote P with subscript x6 because this is the node that I sum, and the new variables are x2 and x5. So I am giving you, so I am going to eliminate node x6, all right? And notice there is a dotted line there. What does the dotted line implies here? So here, basically, the new potential links variables 2 and 5, and that's what I do in the graph. I basically say 2 and 5 are now linked together, all right? And I do this one step at a time, so this is a dotted line, but you will see now in the next step, I am going to make this just a dark line as well, so it doesn't, matter. So here it is this picture, and let's do now the summation on the variable x5. So before we did the summation x6, we got a potential that depends on x2 and x5. Now I'm going to sum on x5, and the summation on x5 is going to operate on this times that. So on this times that, and the new potential will have a subscript x5 because that's what I sum. And what is left? x2 and x3. And what am I doing there? I'm connecting x2 and x3, all right? and then I will get rid of node 5, leading to this. Okay? All right, so let's continue and eliminate now node 4. If I eliminate 4, there is no dependencies that I have to worry. Actually, this summation comes here to be equal to 1. So this potential is equal to 1. So this is eliminated. I get a graph like that. And then if I get rid of node 3, all right, so node 3, there were several potentials that I have generated in between, right? So in node 3, I have x3 given x1, but I have a potential phi of x5 that is a function of x2 and x3, you remember? All right, a function of x2 and x3. And also I have this potential here that's a function of x2. It's equal to 1, but we just keep it for decoration purposes. Where are we? And so we have p of x3 given x1. No, actually I don't keep it. It's times 1 times p of x5 of x2 and x3. I sum in x3, and then what is left is something that depends on your x1 and x2. Okay, and this is basically my marginal distribution that I want to compute. So the marginal distribution is p of x1, p of x2 given x1, and two potentials, one depends on x2 and one depends on x1 and x2. And this, again, the subscripts telling me the nodes that I summed or I eliminated as the algorithm was proceeding. Okay? So does it make a little bit sense? All right? So we will write the algorithm as an algorithm shortly. Okay? So you may want to appreciate, right, that when we sum these terms here, obviously the highest cost in the calculation is the one that involves basically the highest number of variables in this summation. So for example, here I have two variables. So the cost of this, if each of them can take r values, will be r squared, all right, for each value of x3. Here there is only two variables, and here I have two variables, and here I have three variables. So this calculation of this potential will be basically the most expensive in the process, and effectively, so you can actually, you will see later on when we talk about the undirected graphs, basically, that these nodes define the maximum click on the corresponding undirected graph as I do this elimination process. Okay? So I'm going to show it to you shortly. Okay? But for now, I just want you to appreciate that here obviously you have three variables, and you want to sum on x5 for each of the values of these three variables, so this is where the highest cost is. All right? So this will define the cost of the algorithm. All right. This is a nice example. I don't know where I extracted it, but it tells you how important is the way you start. From where do you start doing this elimination, right? You can start from any node, but if you do it wrongly, you can take a trivial problem and make it very painful. So here is a problem. Let's say you have all of these variables, and somebody tells you you want to compute, let's see, let's say you want to, I don't know what you want to compute at the end, right? But let's say we want to eliminate x1, okay, first, right? Maybe you have some evidence and you want to start doing elimination from x1. If you eliminate x1, what happens? I mean, I'm writing here actually the joint probability distribution factorized on the graph, right? If you eliminate x1 first, what's going on? So the dependencies now will be between all variables. All variables depend on everything else. Good luck. You took something that sort of was not looking bad, and now you have a graph that it's fully connected. All right? Not good. And obviously you have to program these ideas, right? So because you cannot go and say, oh, nice graph, do this and do that, because, you know, it's just visually you won't be able to see what's going on. So certainly this is really bad. But look what happens if I go and eliminate, let's say, x3. x3 basically introduces no additional dependencies because the x3 comes only in the probability of x3 given x1, which is equal to 1. So nothing. Nice. Okay? Nice. All right, so before we go back to the to this elimination algorithm to formally state it, so let me, this is sort of actually for decoration reasons, this evidence potentials, but because it's in the books, let's talk about it. So we need sort of to see, at least mathematically, how we write these summations when some of the nodes are clamped down to some particular values, and we denote this as x bar. So if the node I has a specific value, we denote this as x bar I. All right, so that's the evidence we have. So that node basically is can only take that value. All right, that's the evidence, and cannot change. So let's see how we this evidence is going to come on the in various ways on these summations. So let's say, what does it say here? We want to compute P of x1 given the evidence x6, okay? So, you know, we observe the x6, and we want to find what's the conditional of x1 given x6. So obviously, to do this calculation, we have to find the joint of x1 and x6. And I write this as a joint, even though x6, you notice, is prescribed, okay? So what I do is the same trick by pushing the summations inwards in the variables 2, 3, 4, 5. But notice on this conditional of x6 given x2 and x5, you have this probability that corresponds basically to a slice on the three-dimensional table. Right? The values, the x6 can take various values, let's say 0 and 1 here, right? So if I give you that x6 bar is 1, you're going to take only this slice of this table. All right, so this is what this will imply. So when you sum in x5, you're going to define a potential phi x5, and the variables left will be x2 and x3. All right, then you have to sum on x4. So these are the only variables that involve x4. I'm sorry, where is the x? No, actually, so this potential is outside the summation, right? I left it to the right because for no particular reason. So I sum on x4, this is equal to 1. Then I have to sum on x3. This potential depends on x3, okay? So I have the product of those two terms, so it will be a new potential phi x3 of x1 and x2. And then I have to sum on x2, and I have the product of two potentials and this conditional, and I get basically a new potential, which is phi x2, and the only variable left is x1. And if you, so this is the joint, all right? And if you want the conditional, given the evidence x6 bar, is basically this is the final result. Okay? So, so this is sort of a way, one of the ways to calculate the evidence by taking slices of this table. Okay? We don't need this. The other way that you can account for evidence is using sort of delta functions. Okay? So the idea is sort of trivial. I don't think you ever program it this way. But let's say that at some node, you're given the value. So what you do is you assign to that node a potential that you call an evidence potential. And that potential is a delta function that you say, well, you know what? Whatever you do to that node can only take that value. All right? But you treat it as a potential, and you sum over the variables using your elimination algorithm, and you let the delta function do the algebra, the selection of the slice from that conditional distribution without doing it sort of explicitly. So, for example, if you want to write the probability, let's say, of, let's say we have, you know, this probability of x6 given x2 and x5, all right? So effectively, using this evidence potential for node x6, because the node x6 is clamped to this value, you use this potential and you say, go and sum in x6, and obviously this summation for x6 will give you an x6 bar, right? Because that's the only value x6 can take. You don't really program it like this, but you know, if you sort of want to write it in a generic way, mathematical, you can say, if the values are given at the node, assign an evidence potential in addition to the conditional distributions. So when you write the whole distribution, the factorize of the graph, you also multiply with this evidence potentials, and the rest basically in the elimination algorithm is exactly as before. All right. And here basically I generalize this with this evidence potentials. All right, so here's the algorithm, the elimination algorithm on directed graphs. So you have a graph G with evidence C, edges, let me see. So E is the evidence, yes, the evidence nodes, and F are the query nodes. Okay, so using Jordan's notation here. So, so what you need to do is you need to initialize the graph. Okay, basically the graph needs to understand the potentials that you have. You need to introduce the evidence, what nodes have prescribed values, and sort of, you know, the delta functions that we discussed it. Then you need to update the graph given the evidence. So basically, I will assume I have to see the next slide. This is where this elimination algorithm is going to happen. And then effectively, you have to normalize. Let me come back to this, okay? So let's see the details of what these algorithms do, and then we'll come back to this thing on the top. So let's say at the initialization, you choose an ordering. This is very important, an ordering such that the query nodes are appearing the last. Okay? So an elimination ordering basically before what we were doing, so let's say the probability of x1 given the evidence, right? So you want the query nodes to appear the last basically in the elimination order. And in the initialization for each node, you're going to place the conditional probability in the active list of potentials. So you're going to keep sort of an active list that defined all the potentials in your problem, and those potentials to start will be this conditional probabilities, right? You haven't done any elimination, so this is what you start with. And obviously, you need to have an active list because later on, in that active list, you're going to have to introduce these potentials when you do elimination variables, right? So the active list will keep track of all the potentials that define the factorization of your joint in the graph, okay? So you initialize and you create this active list where you put all these conditional distributions. You have to put the evidence. Effectively, for every node in the evidence, you have to place this evidence potential, all right? Okay? And you notice it says here, place the evidence potential on the active list. So you're going to treat sort of these delta functions as part of your factorization. Because when you write the factorization, you're also going to multiply and say, let's say, delta x6, comma x6 bar, because x6 cannot take any other value but that x6 bar, okay? So this will be part of the, all right? So this is what the evidence does, this is what the initialization does, setting these potentials on the active list. And let's see what the update does. So you go through the nodes in the elimination order. You find all the potentials in the active list that contain the node xi, and then you remove those from the active list. Right? Because you remember that there's going to be a summation on xi, and you're going to come up with a new potential, phi of xi, and then you're going to place that phi of xi in the active list. Everything else will disappear from the active list. All right? first is like, you lost that information is gone. You don't need them anymore, all right? So you are going to sum over this. So these are all the potentials, basically, that involve, they have a reference to node xi. All right, so you sum on xi, and you get rid of those products, and you substitute those potentials with phi of xi, okay? And so that's the update. And then, of course, when you finish and you have reached your query nodes, what you need to do is, these are the potentials that only refer to the query nodes except. Obviously, you have to normalize those, all right? And then you're done. Okay? So you are going that way. You're going to compute the conditional distribution of xf given xc. All right. So let me, I don't know how much time we have, right? But let me try to rapidly see if we can introduce here what's going on with graphically when you do this process. So I'm looking again at this summation, all right? To come up with this potential, we had this product that contains xi, all right? And contains the nodes affiliated with, in these potentials with node xi, all right? And these nodes are the nodes that are actually related with what I call the elimination clique in the graph. So I remind you, a clique is a set of nodes, right, that is fully connected, all right? So as the elimination process happens, I have, let's say, a clique of 3 nodes. I integrate over one node, and then I'm left with, let's say, 2 nodes, all right? But the clique that I'm eliminating one node has 3 nodes. That's the elimination clique, and the maximum of these cliques is going to define the complexity of the algorithm. So, so can you look at this, different type of graphs, and think of the elimination algorithm proceeding one node at a time, and tell me which one do you think is going to be more complicated, computationally speaking. Don't look at the definitions, but look at this. If you start eliminating one node at a time, and then you have to do summation over the affiliated nodes with that node. So let's say if you eliminate this node, how many nodes in the potentials are related to this node? How many? So if you write the joint, right, the factorized, and you want to eliminate this, and you sum over that node, how many in the potential that you're going to be doing the sum, how many other variables are involved? I mean, think here, right? What are you going to have? You're going to have the probability of this given that, and then the probability of that given that. So how many nodes involve this? How many terms do we have? How many? How many? How many terms this x25, let's say, comes from? 1. All right. So, so what we do is, if you look carefully, it says here, we define the treewidth as the minimum size over all possible eliminations of the maximal cliques created during graph elimination minus 1. So the clique here is size 2, all right, because there are 2 variables, minus 1. And we put the minus 1 because this is a tree structure, and we want to have this variable that for trees is equal to 1. All right? So in this case, basically, this is the only potential, that you will work with. So this is the clique. The clique is of size 2, minus 1, the treewidth we define to be equal to 1. How about here? So if I want to eliminate this, All right? What is going on? Well, actually, let's take something more, take something more complicated. Take something here. What do we, how many things we need to eliminate? So if you try to eliminate this, well, we have to do something in sequence. So let's see, which should we eliminate? I mean, consider that this thing goes up and down, right? So it is a two-dimensional graph looking like that. So it doesn't matter. Let's concentrate on this node, and let's say we have eliminated this. So how many potentials, how many variables we have to eliminate? What is the elimination click where the summation is going to operate? How many nodes will involve, let's say, this node? We assume this already we eliminated to the right. How many? How many? I heard it. 3. So 3 minus 1, so the tree width is 2, and etc. More complicated case. So obviously the cost of the calculations, if every variable can take k values, the cost at every node is k to w plus 1, where w is the tree width, and then times v. This gives you the order of the cost of the calculation. If you don't do the elimination algorithm, basically the cost will be k to the power v. All right, v is the total number of nodes. So obviously this is linear in v, so it's v times k to w plus 1. And lots of times, I think in some earlier lectures, we didn't put the plus 1 because if w is big, the 1 doesn't make much difference, but this is the sort of the correct calculation. Okay. So let's look at this in the context of undirected graphs, okay? I mentioned we're going to be here a little bit so we can unify the directed and undirected graphs. We're going to be sort of a little bit ahead of ourselves because I haven't discussed the factorization of the joint distribution over undirected graphs. But let me just state it, all right? So again, we're going to be a little bit ahead of schedule here, and we will come back to this in details. In directed graphs, remember we had the probability of every node x given its parents. In undirected graphs, the joint probability distribution is factorized in terms of potentials defined over maximal clicks. So you find, all the possible, basically, maximal clicks that you have in your problem, and this is the biggest number of interconnected nodes. So, for example, is x1, x2, x5, x3 a click? No. Why? Because x1 and x5 are not connected. Because x2 and x3 are not connected. So really here what you have is, if this is an undirected graph, you have this click, you have this click, you have this click, and then you have a click of 3, and then you have a click of 2. So each of these clicks comes with a potential. Not a distribution, just a potential of those functions that sort of express how strongly variables are correlated in that click, right? But they're not distributions, they're potentials. So, so let's, if you're trying to do eliminations on undirected graphs, the algorithm actually literally is a copy carbon of the algorithm for directed graphs, but it's a little bit less complicated because there is no errors or anything like that. So what I have done on this graph, I took the joint distribution, I wrote it in terms of potential over maximal clicks, as I just told you, all right? I plug in the evidence, as you see in here, okay? And then to find this joint, I pull the summations all the way to the right so they start applying to the correct terms. And exactly as we did with directed graphs, the notation is practically identical. The only thing that you see that is different here from what we did with directed graphs, when you write these joint probabilities in terms of these potentials, this factorization does not give you a normalized distribution. So the normalization factor basically there is not known. But eventually when you do the algebra, all right, and you compute this joint, and you want this conditional, You don't really need Z because once you get this potential, this is basically this conditional distribution. Anyways, what we're going to do is, so these kids can invade the room, we're going to see this in action, and then we're going to merge the two algorithms and give you sort of a graph theoretic approach with elimination of cliques that will do the elimination algorithm. So you don't really have to say, do this over variables, but basically you're going to start eliminating nodes, while at the same time you keep track of the cliques where these nodes are eliminated. There will be some marriage of summarization process happening in the process and some other weird things, but they will all be graph theoretic approaches. So we'll do operations on the graph, not on the distribution anymore. Okay? So the notes are up actually, so you can read, you can be ahead of me, and I will see you on Thursday, and if I remember, there's a homework due sometime in the very near future. Okay, so for any questions in the homework, talk to Shubik.